Hi, in this video series I will be explaining Chapter 7, Taylor expansions and finite expansions. What we will learn in this chapter is an essential tool that can be used to study approximation of functions by polynomials. But first, why do I need to approximate functions by polynomials? In fact, every physical problem or every solution to any physical problem, like if I want to calculate the movement of water following a given incident in water, or if I want to study the movement of the airplane when it's flying, or if I want to study the deformation of the body of a car when it hits a wall or it has an accident. So every physical problem I want to study, its solution is a function that represents what will happen in the reality. But this function is not a polynomial. It's neither any usual function I know. It's not a logarithm, not a cosine, it's not a sine, it's not something that I know. So in order to understand and to represent what will happen in reality, I need to find an approximation of the real function that represents the real solution. And this approximation, usually I look for a polynomial approximation, because polynomials are easy to deal with. They are easy to differentiate, easy to integrate, etc. Easy to evaluate even with respect to other functions. So it's always interesting to study the approximation of functions by polynomials. Let's start by a introductory example. We know that 1 minus xn plus 1 can be written as 1 minus x times 1 plus x2 until xn. Because if you expand this part, you will have what's in here. In fact, all the terms will cancel except 1 and xn plus 1. So, according to this, we can write 1 minus xn plus 1 over 1 minus x is equal to 1 plus x plus etc. plus xn. But if n tends to infinity and if x belongs to minus 1, 1, then this term in here will go to 0 when n tends to infinity. Okay, so we will have the equality 1 over 1 minus x being equal to this term as n tends to infinity. That's why I will write 1 over 1 minus x is equal to the limit of 1 plus x2 until xn. Now, if we look at this equation, we can interpret it as a polynomial approximation, because what's in here is a polynomial, and what's in here is a function that is not a polynomial. So on the right side we have a polynomial that's almost equal to the function, but it will be equal to the function when n tends to infinity, which is not something real. I mean, if we take, for example, 1 over 1 minus x on one side and 1 plus x plus x2 plus x3 on the other side, these two are not equal because n in here is only 3. We didn't go to infinity. But they are equal if we add or subtract an error. So we can say somehow that these two are equal, but there is an error that differentiates them. So they're not really equal, they are approximately equal. And this error is all the remaining terms. So this error is the x4 plus x5 plus x6, etc. until x infinity, right? So what we can understand from this also, that if we take n greater than 3, so if we say that 1 over 1 over 1 minus x, is equal to 1 plus x plus x2 plus x3 plus x4 plus x5 plus error. So the error in here, it represents the terms from x6 until x infinity. So we can suggest that this error might be less than this one because it represents a smaller number of terms. Okay, so what we should understand from all this is that we are able to write an approximation with a polynomial to this function, which is not a polynomial, and we can accept this approximation if the error is small enough. Let me give an example to understand what does it mean to say the error is small enough. If we calculate the example of a car hitting a wall, let's say. So we have this car that will hit a wall, right? This is the wall. So when the car hits the wall, you have the hood in here that will be deformed. So after the accident, it will look maybe like this, right? So if you want to approximate the shape of the hood after the accident, okay, you can find a function that approximates the shape. The function might be a second degree polynomial doing like this, right? What's interesting for you is that the hood took this shape and it absorbed all the shock. So the shock didn't went to the passengers inside the car, but it was absorbed by the hood. So I don't care if really the shape of the hood is like this or if it's like this, right? What matters, it's that globally it's taking this shape, right? So it absorbed the shock. That's why I'm saying that if I approximate with a second degree polynomial, it's enough for me that the extra terms that represent the error will be all the terms that represent the errors between the second degree polynomial and the real shape. But this real shape, it doesn't matter for me in this case. Okay, so in this case or in this study, I don't really care about these errors. They doesn't matter for my study, so I can accept the error that is being or that's obtained by the calculation, or that I am committing when I'm doing my calculation and my approximation, of course. Now going back to the approximations, let me take one more example, the exponential x. The exponential x can be written as the limit of 1 plus x over 1 factorial 1 plus x2 over factorial 2 plus etc. plus xn over factorial n. And this equality can be proved using the Newton binomial formula. Now we don't need to prove it. I'm just saying that it can be proved like this. So maybe if you are interested, you can look for it, how it can be proved using the Newton binomial formula. Because now in this chapter, I will show you how I can prove it in a different way. So here also we can say that this equation is an approximation of the exponential function. And it's very interesting because the exponential function, it cannot be calculated numerically in another way. So to calculate it numerically, the easiest way is to calculate the value of this polynomial. And so I'm saying in here that if you take n equal 3, then exponential x will be equal to 1 plus x2 over 2 plus x3 over factorial 6 plus an error that represents the remaining terms. So it's a polynomial approximation of the exponential function. So let me now inspect these two formulas a little more. If I take the first one, taking f of x being 1 over 1 minus x and Pn of x equal to 1 plus x2 plus etc. until xn. So the f of x minus Pn of x, which is 1 over 1 minus x minus the error. So the error is represented by 1 minus xn plus 1 over 1 minus x. So this is what I showed you in here. So because the polynomial in here is this term. So if I subtract 1 over 1 minus x, I will have xn plus 1 over 1 minus x. So this is the error that remains in here. And what's important is that if n tends to infinity, then xn plus 1 will go to 0, as I said. So this is the error that will go to 0. So you have the error term that goes to 0 if n becomes big. So as n increases, the approximation should be better. Let's look a little bit to the graph of this approximation. Here you can see the function f of x in here in green, and the different polynomials for different values of n. So if n is equal to 0, if I take n equal to 0 and I draw the polynomial, it's in here. N equals to 1, it's in here. E equals to 2, equals to 3. And you can see that as n increases, the approximation is better. So for n equal 3, you are approaching the function. But for n equal 4, you are closer to the function. Of course, the n equal 4 in here is for the blue function. and the n equals 3 is for the yellow function. We have also the same behavior for the exponential function. For n equal 1, you are approximating the function. So at 0, you are going through the function. Here you have a big error between the approximation and the function. But for n equal 2, n equal 3, so you are closer to the function. Even for n equal 3, you are very close in this interval from here to here. So now if you take a bigger interval, you will have errors that will propagate through x. But if you increase n, you will approximate the function in a better way, even if the interval is big. So what we mean by approximation is that if you take a number x, let's say, I don't know, -4, you take exponential x, and the value of the polynomial at this point x, you will have very similar values. Go try to do some calculations. Try to take n, for example, equal 5, and calculate exponential, I don't know, 10, using the polynomial and the exponential, and you will see that you will have very similar numbers. So the question now is how to compute these polynomials. For these two functions, 1 over 1 minus x and the exponential x, we found a way to calculate the polynomial or to compute the approximation. But in general, how can we be able to calculate these polynomials that will approximate the functions even locally around a point? When I say locally, I mean it's an approximation around a given point, in the neighborhood of a given point, and not for any x in the domain of definition of the function. So we start to find the idea by calculating the derivative of a function. So if I take the derivative of a function f at x0, so it's the limit when x tends to x0 of f of x minus f of x0 over x minus x0, which can be written also f of x equals to, so I multiply x minus x0 by f prime, and then I add f of x0, and then if I want to remove the limit, I should add this kind of terms. Why? Because if you put again the limit, if you put the limit on both sides, so you will have the limit of this term equals the limit of this term plus the limit of this term. So again, if you have f prime of x0 equal f of x minus f of x0 over x minus x0 plus a limit in here, so you can remove this limit by adding a term epsilon of x minus x0, such that this term should go to 0 as x tends to x0. So if you put again the limit, if you say that, of course here it's a number because it doesn't depend on x, it's f prime on x0. So even if you put the limit in here, it will stay f prime at x0. But if you put the limit in here, so you'll have the derivative plus this will go to 0 by definition. So I'm saying again, if you remove the limit, you can remove it and keep the equality, but by adding a term in here that goes to 0 when x tends to x0. Now if we redo the calculation of f of x as in here, we will obtain x minus x0 times epsilon x minus x0 as a term in here. Okay? So if you look closely, you will find that your function f now is a constant plus a first degree polynomial, x minus x0 times f prime at x0. So it's like you are saying that my function, whatever the function is, it can be an exponential, a logarithm, any function. Of course, it should be differentiable. So it can be written as a first degree polynomial plus a term that should go to 0 as x tends to x0. So it means that if you take your function, that maybe it's like this, and then it's equal to this term, which is the tangent. This is the equation of the tangent at the point x0, right? So this is the tangent. I'm saying that the function is equal to the tangent, right? It's equal at the point itself in here, it's equal. But if you move from this point, you will have an error between the function and the tangent, and this error will be represented by this term. So this term will go to 0 as x tends to x0 because at x0 you have the equality, and if you move far from x0, you have the error between the function and the tangent that is represented by this term. So it makes sense to say that in here we are approximating our function by a first degree polynomial, and the error is of the or can be written as x minus x0 times epsilon of x minus x0. So now to go further, to see how can I can approximate the function with a polynomial of degree greater than 1, because 1 is not sufficient. You are approximating a function by a first degree polynomial, by the tangent. So to go a little bit further, I will say that I will choose the polynomial Pn of degree n such that I should have the derivative of f at the point x0 should be equal always to the derivative of the polynomial at the point x0. Why is that? Because let's take, for example, the first degree case in here. If you take the derivative of f on the other side, this term will be equal to 0, its derivative. And this term will be equal to the derivative of the polynomial at x0, which is f prime of x0. You see, it's the derivative of f. So it's equal to f prime. I mean, so if you take your polynomial such that the derivative f prime is equal to the value of the polynomial at the point x0, and then the second derivative equal to the second derivative of the polynomial also, because this term in here will be equal to 0, or will be, when I calculate the second derivative, this term will vanish, will be equal to 0. Then you will have the third term that will show the second derivative of Pn that should be equal to the second derivative of f. So I will choose my polynomial satisfying this, or written as follows. So you see, this polynomial, if you take the second derivative of this polynomial, it will be equal to the second derivative of f. Of course, in here I'm taking x0 is equal to 0 because this is the case that we will study the most throughout the chapter. So if you take the third derivative of Pn, it will be equal to the third derivative of f at 0. So the 2 in here will go will be simplified by the derivative of x2, so the 2 from the exponent, and the 3 as well, because in here we have f triple prime at 0 over x, times x 3 over factorial 3. So the factorial 3 will be simplified with the second derivative coefficients, which will be 3 and 2. Okay, so all this is an introduction. So everything I said will help us to understand why we are writing such expressions and why we are calculating the approximations, and from where we have this kind of expression that contains the factorials and the derivative of f. But now we will state the theorem that you really should know and we will really be using. So recall now that I will take f as a function from AB included in R into R, and I call this function a CP function if and only if its derivative to the order P, all its derivatives are continuous, exist and are continuous. And when I say that this function is C0, I mean it's a continuous function. So let me state the Taylor-Young formula, or the Taylor-Young theorem. So if I take f as a real function such that f is defined and continuous on an interval a plus h, it's Cn minus 1 on a plus h, so it has at least n minus 1 derivative, continuous derivatives, and f is n times differentiable at the point a, so it's not only Cn minus 1, it has an n derivative which might not be continuous, not necessarily. Then we can define on the interval a plus h a function epsilon such that f of a plus h is written as f of a plus h over 1 f prime of a plus h2 over factorial 2 f double prime of a plus etc. until hn or factorial and fn of a plus hn epsilon of h, where epsilon of h goes to 0 as h goes to 0. So this is exactly what we wrote before, because if you replace a plus h by the point x that we had before, and if you replace a by the point x0 that we had before, the formula that can be written f of x equal f of x0 plus x minus x0 over factorial 1 f prime at x0, which is the equation of the tangent, plus the remaining terms, plus hn, which is x minus x0 power n epsilon of h. So it's exactly what we were writing before with the tangent approximation, but we are adding more terms to the approximation. So we say in here that if you write this expression in here, the error will be something that can be written as x minus x0 to the power n times something that goes to 0 as h goes to 0. And this is exactly a polynomial approximation, because here you have a constant, a first degree term, so it's something that contains an x, and then you will have here a second degree term having x minus x0 power 2, which is in here, and etc. But usually it might be sometimes easier to represent it like this. Okay, I mean with a plus h and h. So the term h n epsilon of h is called the remainder of the Taylor-Young expression, and the term f of a until hn of factorial and fn of a is called the Taylor polynomial. So now, of course, you can replace a plus h by x, as I said, and it will be f of x equal f of a plus x minus a over 1 f prime of a, etc. And this way you will see clearly the x, which for you are used to it as the variable of the polynomial. So here you can see clearly now the polynomial function of x, and here you will have as the remainder x minus a power n epsilon of x minus a, where epsilon of x minus a goes to 0 as x tends to a. Now for the proof of this theorem, you don't need to know it for your exams and for your course, so I'm not going into the details, but I wrote it in here in case someone really likes to read it. It's a nice idea because it's based on the fact that we can do the proof by induction, and we can do it for f prime and then integrate to obtain the formula for f. So it's a nice proof. You don't need to go into the details, the technical details of the existence of the function epsilon in here, but at least you can read the induction idea. It's a very nice idea. Now let us state another theorem that says that, okay, the Taylor-Young formula gave a polynomial expression with a remainder, and the remainder, all we know about it in the Taylor-Young formula is that it's x minus a to the power n times something that goes to 0 as x tends to a. But we can go further and we can prove that this remainder is in fact a function of higher derivatives of f. So this remainder can be written as in this expression. To understand the idea a little bit, in the Taylor-Young formula, the remainder was h to the power n epsilon of h, right? So it was like this, but we said that epsilon of h goes to 0 as h goes to 0. So if epsilon of h goes to 0 as h goes to 0, so it's h times something, of course, because otherwise it will not be able to go to 0. Of course, it's a polynomial form. We know that it should be a polynomial form, because if we take a higher order polynomial, the terms that will go out from the epsilon will be polynomial. Let me say it again. If you take this expression to the order 3 and then you write the remainder, whether in the Taylor-Lagrange or the Taylor-Young formula, the remainder, it's a hidden box. We don't know anything about it, but we know that it goes to 0 as h goes to 0. Okay, great. But if you write this formula to the order 3, let's say, and then if you write it again to the order 6, it means that you took out from the remainder some terms, you added them to your polynomial, and then your new remainder is what is left in the remainder, right? So when you're taking out these terms, they are showing up in the regular part in here as polynomials or polynomial terms. So your remainder, really, it's a polynomial, but you have n that goes to infinity, so you cannot represent it as a finite number of monomials. That's why we are saying it's a polynomial form. So since it's a polynomial form and it goes to 0 as h goes to 0, so it must be h times something, of course. So at least you have h. You have h2, h3, h4, etc. But at least you have h in it times something. So this h and the hn in here, they will give hn plus 1 at least. So you would have hn plus 1 times a higher order derivative. So we can prove this, that it's a higher order derivative. So it's n plus 1 or greater at a given point c, and c should be a point within the interval a plus h. So this is the Taylor-Lagrange formula that we can prove also by induction. Also, this proof is not, it's not necessary to know for you. It's not in your syllabus for your exams, but you can read it if you would like to know a little bit better about the theorem. So is this fn plus 1 of c, is it a bit strange for you? It should not be, because if you take n equals to 0, you will have f of x equals to f of a plus n equals to 0. So that's it for the polynomial part. So now it's the remainder that will be written as x minus a to the power 0 plus 1, so power 1, over n plus 1, so it's 1, times f prime at a point c. So if you look at this Taylor-Lagrange formula for n equals 0, it's exactly the mean value theorem. So the existence of an expression like f prime of c or fn plus 1 of c is not very strange for us, because it's exactly the mean value theorem, and by induction we can prove the theorem for any order n. Now, of course, if we replace a plus h by x as we did before, you will have this kind of formula. It's the same as Taylor-Young, but the only difference is that we are expressing the remainder as a polynomial part times a higher order derivative of f at a point c. Let's take, for example, the function sine. So sine h will be written as h minus h3 over factorial 3 plus etc. plus minus 1 to the power n minus 1 to h to n minus 1 over 2n minus 1 factorial. So why you don't have an h2 in here, for example? Because this term, the h2, will be multiplied by the second derivative of sine. So it's sine squared at the point 0, because here we are calculating sine 0 plus h, so a is equal to 0. And the second derivative of sine at the point 0 is sine at 0, which is equal to 0. So we have all the even order terms that vanished. So we are stuck only with the odd terms. And at the end we have the derivative of sine, the n plus 1 derivative of sine, which is sine c plus n pi over 2, because we proved, if you remember, in that the differentiation chapter, that the derivative of sine, the n plus 1 derivative of sine, x is equal to sine, of course at a point x0, let's say it's equal to sine x0 plus n pi over 2. This is something we proved earlier. If you take the function exponential h, so exponential 0 plus h is equal, so you apply the formula, try to do it, you will obtain this kind of functions. And of course the derivative of the exponential function is ex, so at the point c it's e to the power c. Now if you apply the Taylor-Lagrange formula now on the interval 0x, so now a is equal to 0 and a plus h will be equal to x, then you obtain what we call the Maclaurin formula, that is written as f of x equal f of 0 plus x f prime of 0, etc. And at the end, instead of writing c in the Maclaurin formula, we are writing theta x, where theta is a number between 0 and 1. Technically, we are replacing c by 0 plus theta x. Of course, if theta is between 0 and 1, theta x will be a number between 0 and x. So it's only a representation of this number as a function of x.